In this series of lectures on relativity, titled Relativity with a Flashlight, I'm going to try to describe the basics of the special theory of relativity from a slightly unorthodox viewpoint. Unorthodox in the sense that I'm going to stress a method of exposition where the physical meaning of what is happening should be clearer than, say, the standard approach, which essentially relies on writing down something called a Lorentz transformation and getting all the properties of relativity or all the features of relativity out of that. I actually believe that the physics behind this particular subject is very, very important, and unless we pay attention to what is happening behind the scenes and rely only on the algebra, we will be missing much of the fun of it. So this is really more of an attempt to make relativity fun. And as you can see from the date on the slide, this is a very old lecture. In fact, this is a later version of the original lecture. The original lecture was prepared in the year 2005. Many of you actually already know what the significance of the year 2005 is. This was declared as the International Year of Physics, primarily because of the exploits of one man, a young Swiss patent office clerk who had published 4 miraculous papers in just 1 year, exactly 100 years before this. Each and every one of those papers were potent enough to change the face of physics forever. The young man I'm referring to is, of course, none other than Albert Einstein, and his annus mirabilis or miraculous year was celebrated all over the world, and we in our small way tried to describe his work to school students at the time. Since then, this lecture has been delivered several times on several occasions, with slight modifications, of course. But it has been a rather long time since I have actually come around to giving this series of lectures. A year ago, I uploaded a version of these lectures, at least a part of these lectures in Bengali, and quite a lot of my friends and students asked for an English version. I had not been able to get round to that for other preoccupations, but now I think I will give it a go. So, hopefully over the next few lectures I will be able to take you on a trip of Einstein's wonderful physics in a slightly different way from what you would find in a standard textbook. But rest assured, all of this is very standard physics. None of this, of course, is my invention. Even this particular mode of exposition is actually quite standard. It's available in textbooks. It's just not the mainstream method that one usually finds adopted in most textbooks. Now, while discussing relativity, it is often customary to start with a discussion on its historical underpinnings. What discussion of relativity would be complete without a rather lengthy discussion on, say, the Michelson-Morley experiment? I can spend a lot of time, hours in fact, talking about the approach which ultimately brought us the theory of relativity, but I'm going to not talk about all that in great detail, except for some very few short words. Let me first introduce you to the person who founded the principle of relativity. And no, he is not Einstein. This was long before Einstein, in fact. The actual founding father of the principle of relativity was none other than Galileo Galilei, who had stated his result in a rather poetic manner in a rather lengthy story format, but the gist of it all can be sort of boiled down to this one simple succinct statement. It is impossible by any purely mechanical experiment to distinguish between rest and uniform motion. And this is the principle which was behind what is called Galilean relativity today. This was the first statement of the relativity principle, which essentially tries to put all observers on the same footing. And what Galileo was saying is whether an observer is at rest or whether he is uniformly moving should not make any difference as far as mechanical experiments are concerned. Another way of putting this would be simply to say all laws of mechanics are equally correct in all inertial reference frames. Now, immediately after Galileo, the major player in this scenario was, of course, none other than Isaac Newton. The followers of Newton had a small amount of difficulty with this principle. After all, Galilean relativity puts all inertial observers on the same footing, does not put one inertial observer above the other. On the other hand, Isaac Newton was a great fan of the idea of a absolute rest observer, one observer who is in some way different from all other observers. Now, this is of course something which Newton's own principles of mechanics, which were consistent with Galilean relativity, were not really in support of. But Newton's followers actually had a way out. They simply said, okay, fine. It is true that as far as the laws of mechanics are concerned, all inertial observers have exactly the same status. But physics is not only mechanics. There are other things besides that, and there are special preferred frames, or in fact, one special preferred frame in which all laws of physics will become very simple, and that will be the absolute rest frame. Now, while there is a lot of experimental evidence that accumulated over the years which ultimately was instrumental in Albert Einstein's thought process, it is really true that Einstein's primary objection to Galilean relativity was on a philosophical point. In fact, it was on this particular philosophical point he took quite the opposite route to what the followers of Newton's would have said. So what Galileo had said was all laws of mechanics are equally correct in all inertial reference frames. What Einstein said was all laws of physics are equally correct in all inertial reference frames. Here this philosophical objection towards having a very important principle, the principle of relativity, which according to him was a beautiful principle, too beautiful to give up, limited to just mechanics. He said that if such a principle is going to hold, it should hold for all of physics or not at all. After all, there is no such thing as a purely mechanical experiment. If you want to see the result of an experiment, you have to use light, so optics comes in. Basically, what he was saying is he was giving Galilean principle of relativity much bigger importance. He just said that it has to work for all of physics, not just only for mechanics. At this stage, Einstein was faced with a bit of a problem. This principle of Galileo, that the laws of mechanics are the same in all inertial frames, was not just a philosophical principle. There was some very strong mathematics behind it. Galileo and his followers had developed a way of figuring out how observations by one inertial observer can translate to the observations made by another one. These were called the Galilean transformations. It so happened that if you applied the Galilean transformations, all the laws of mechanics retained their form. The technical term here is the laws of mechanics are covariant under Galilean transformations. Note the choice of the word covariant rather than invariant. An equation, a law of physics is after all an equation. There are two sides to it, and we are not claiming that the equation does not change. All we are claiming is that when we apply the Galilean transformations to translate the measurements made by one observer into the measurements made by another, both sides of the equation change equally. They co-vary. So if the equation is correct for one observer, it has to be correct for another. Now, the laws of mechanics are Galilean covariant. And that is why Galileo could claim that the laws of mechanics are equally correct in all inertial frames. It also turns out that the laws of electromagnetism, on the other hand, are not covariant under Galileo's rules for transforming from one frame to another. That is, they are not Galilean covariant. This, of course, was very good news for Newton's followers because they could claim that there is only one inertial frame in which the laws of electrodynamics becomes very, very simple, and that is the proper or absolute rest frame that they were all seeking. Now with Einstein, with his insistence on the law of relativity being valid for all of physics, had this problem at hand. He could definitely accept the Galilean transformations as the correct way of transforming from one frame to another, and then there would be no problems whatsoever with the laws of mechanics as they were written. But what he would have to say is that the laws of electromagnetism needs to be rewritten. On the other hand, he could equally well have claimed that the laws of electromagnetism are actually the correct laws of physics as written. And what that means is that the transformation of frames written down by Galileo, no matter how obvious they seem to be, must be changed to something else, so that under these transformations, the laws of electromagnetism become covariant. But then, under these new transformations, the laws of mechanics would not be. So, either you have to keep mechanics intact and change the laws of electromagnetism, or keep electromagnetism intact and change the laws of mechanics. Of course, you could just as well say that perhaps the principle of relativity is actually not valid for all of physics, but that is something which Einstein was not ready to accept. Now, faced with a question like that, a lesser mortal would have perhaps voted in favor of the laws of mechanics being the correct laws of physics. After all, the laws of mechanics had been around for centuries at that point of time. Maxwell's laws of electromagnetism had been written down properly only for half a century or less. However, Einstein was very, very aware of the experimental situation in physics, and he put a huge amount of stock in the fact that physics, after all, is an experimental science, and everything that you say has to have experimental observable bearing. And he was very aware of the fact that every statement in physics, no matter how beautiful, is really not at all a useful statement unless it can be verified experimentally. He was well aware that the laws of mechanics had been tested and found correct. So had the laws of electromagnetism. But the laws of electromagnetism had been tested to a much higher degree of precision. After all, it is much easier to do optics experiments precisely than do mechanics experiments at the same level of precision. And every time you verify a law of optics, you are actually ending up verifying a law of electromagnetism. So what Einstein saw was, despite the fact that the laws of electromagnetism had been formally around for less time than the laws of mechanics, they had been tested to a much higher degree of precision. So he gave his vote in favor of the laws of electromagnetism as being correct laws of physics, and at the same time, of course, accepting the fact that in such a case you would have to change Galilean transformations into something else and modify the laws of mechanics, Newtonian mechanics, into new laws so that the entire structure becomes covariant under this new transformation laws. So what Einstein did was to essentially encode this in his second postulate. Einstein's second postulate reads the speed of light in vacuum, c, is the same for all inertial observers. Now, if you did not know the background, this may seem a bit strange. Why suddenly the speed of light? Why not something else? But what you must realize is that the speed of light in vacuum is something which is predicted by Maxwell's equations of electromagnetism. So when Einstein was saying that the speed of light in vacuum c is the same for all inertial observers, what he is really saying is that the laws of electromagnetism as written down by Maxwell are correct for all inertial observers. So this was his way of voting in favor of electromagnetism as opposed to Newtonian mechanics. Now there is a lot more to the history of relativity beyond just this much, but I will not really spend any more time on the history. What I will do is show that once you accept these two principles of special theory of relativity, you can, by very elementary physics considerations, derive many wonderful new results. In fact, figure out all of what we call the special theory of relativity. And that is what we are going to turn to now. With this bit of background out of the way, let us now turn to the question of understanding what these basic principles of relativity actually are telling us. And in order to start our process of understanding, I will begin with a very, very simple question. A question which can be posed at the level of, say, class 7 or class 8. And this is a query on relative motion. On the screen you can see a picture of me walking on a road. Now of course I don't have very good graphics skills, so you will have to imagine that the stick figure is me. I'm walking down the road towards a lamp post, the thing drawn in blue on the right, and my friend crosses me on a bicycle. Okay, I originally meant a bicycle rather than a car, but drawing a bicycle was much more difficult, so with my limited graphic skills, I actually settled on drawing a car. So my friend, who is driving a car, let's say, crosses me, goes to the lamppost, reaches the lamppost, remembers that he has something to tell me, and comes back from that point to me. I, of course, have been walking all the time towards the lamppost. So this is what the scenario is like. This is where my friend is crossing me, then reaching the lamppost and turning back from there and ultimately reaching my position. The question that I have for you is this. If you just count the journey of the car or my friend from the point when he crossed me for the first time to the lamppost as the first half of his journey, and back from the lamppost to me as the second half of his journey, which half of the car's journey is longer with respect to me? From me to the lamppost or from the lamppost back to me? I will let you think about this for a little while. Unfortunately, in a recorded video, I cannot really directly ask my audience this question, but let me tell you that the response of most of my audience whenever I have asked this question to a live audience has been that it is rather obvious. The first half of the journey from me to the lamppost is longer. The second half from the lamppost back to me is shorter. And that is sort of justified very easily by the fact that I have been moving towards the lamppost all the time. However, let me stress once again, the question was which half of the journey was longer with respect to me. So let's try to take a look at this same situation from my viewpoint. The view from my frame would be something like this. I would be completely stationary. It's the lamppost which would be coming towards me. So the car would cross my origin and go to the lamppost. So how much does he move from my origin to the lamppost? And then on the return journey, the car travels back from the point where it met the lamppost, back, where else? To my origin. Of course, the lamppost has been coming closer and closer to me all this while, but I'm not really interested in what the lamppost is doing. What I can only tell you is that with respect to me, the journey was from my origin to where the car met the lamppost and back from that very point to my origin, which has not moved with respect to me at all. So, with respect to me, both halves are equally long. Now, did you get this one right? If you did, congratulations. But let me also tell you that many people actually get this wrong. And I can't really blame them. The fact that many people actually say that the outward journey from me to the lamppost was longer and the return journey was shorter is actually a sign that they are thinking in terms of distances relative to the ground. Despite the fact that the question did clearly say which half is longer relative to me, we usually find it very difficult to think of other people's points of view, anybody other than the standard observer whom we have always assumed to be the one who is fixed to the ground. In fact, if you throw your mind back onto all these chapters you have studied about relative velocity, you will find that there is an inherent bias in most of the problems that you read there. There are questions like, the rain is falling at this and this velocity, you are walking at this and this velocity, you get to meet the rain at this angle. So what is the actual direction of the rain? Now, of course, what is really meant there is what is the direction of the rain with respect to the ground. But somehow that is the one which we usually refer to as the actual direction. So despite the fact that relativity, Galilean relativity for mechanics, and even more so Einsteinian relativity for all of physics, has taught us consistently that all frames should be treated equally, we almost never do that. And if you have actually voted in favor of the outward journey being longer, you have simply fallen in the same trap. You have taken the observer who is fixed with respect to the ground as more sacrosanct than me, the one who is doing the observing here. So, the lesson that I want you to take away from this is space measurements are relative. While the outward journey is actually longer than the inward journey with respect to the ground, they are equally long with respect to me. Now, which one of us is right about this? The answer is we are both right. Space measurements are not absolute. They can very well change from one observer to another. But what about time measurements? If I now ask you that my friend had driven equally fast on both halves of the journey, then which half of the journey is longer as far as time is concerned? Of course, you should have no difficulty in saying that with respect to the ground, the outward journey should take more time, simply because it's longer, and the inward journey takes less time because it is shorter. So the fellow on the ground would say the outward journey takes more time, the inward journey takes less time. Fine. What will I say? To me, both halves of the journey are equally long. But what I would say is exactly the same thing. I would say the outward journey takes more time, the inward journey takes less time, because what I would end up saying is the velocity that I should use for the car is the velocity of the car in my frame, relative to me, so to speak. So the outward journey of the car was made at a smaller velocity and the inward journey was made at a higher velocity. As a result, even though the lengths are equal, the speeds being different ends up giving you the same conclusion. The outward journey takes more time, the inward journey takes less. And this sort of bolsters our notion that time measurements are absolute. But this is where our first major question comes in. Are they really absolute? And this is what I need to address specifically in the light of Einstein's postulates of special relativity. In case you're wondering why you're just staring at a blank screen right now, it is simply because I cannot afford a special effects artist. If I could have, then what you would have seen on your screen right now is maybe a splendid display of fireworks. And instead of hearing me drone on, you would have heard drum roll. For the simple reason that now is the point where the hero of our story is making an entry into the scene, so to speak. So without further ado, let me introduce you to our hero, a flashlight. Now, just in case some of you may be unfamiliar with the term flashlight, this is what we in India usually call the electric torch or just the torch. Flashlight is what Americans typically call the thing. So, what I'm going to now assume is the same scenario as a while ago. I'm still walking down the road. I have nothing better to do. I'm walking down the road, but instead of a friend in a car, I'm carrying a flashlight, and I switch on the flashlight so that a pulse of light shoots off in the forward direction, that is in the direction in which I'm walking, and instead of the lamppost, there's a mirror on the side of the road for whatever reason. So the light bounces off from the mirror and comes back to me. All the while, of course, I'm walking towards the mirror. The question, again, is very similar. The question is, which half of the flash's journey is longer with respect to me? From me to the mirror, or from the mirror back to me? And by this time, I'm pretty sure all of you have caught on to the issue. With respect to me, I am not moving. It's only the flashlight which is traveling towards a moving mirror, bouncing off the mirror at some point and coming back to my origin. So the answer, despite the fact that the fellow on the ground would say that the outward journey is longer in space for the flashlight as well, I will not agree. I will just say the inward journey and the outward journey are equally long. Now, once again, what we have seen here is space is relative. Fellow on the ground says the outward journey is longer in space. I will say both journeys are equally long. But now comes this important point. According to the fellow on the ground, the speed of light is same on both halves of the journey. So what he is going to definitely say is that light took more time to go out to the mirror than to come back in. So the outward journey takes longer. Now what about me? What I will say is both halves are equal in length, of course. But now note that as far as I am concerned, the speed of light is also equal on both halves of the journey. So the escape route that we had when we were talking about my friend in a car, that the speed of the car when it drove away from me was less with respect to me than when it came back towards me, that is no longer available here. What I have to say is speed of light is the same on both halves, and hence both halves take exactly the same time. Now I don't know whether you have realized this, but we have actually revolutionized our notion of space and time here. Earlier what we had said was two different persons, different observers moving differently, disagree about spatial extent of journeys. And that is something which we can very well live with. But they still agreed on the time it takes. According to the fellow on the ground, the outward journey for the car took longer, the inward journey took shorter. According to me, as I am moving along the road, exactly the same thing happens. And that is because, as we have said, at least in classical physics, pre-Einsteinian physics, time is absolute. But now notice what has happened. The moment we accept Einstein's postulates, in particular the postulate that the speed of light is equal for all observers, now we have this issue that for the fellow on the ground, the outward journey takes longer, the inward journey takes shorter in time. For me, both halves must take equally long. That means my time measurements must disagree with the time measurement of the fellow on the ground. At this point, let me also clarify that the reason why we do not notice this discrepancy in our daily world should also be pretty clear from this scenario. After all, if I am moving along the road, the reason why the outward journey and the inward journey are different for the fellow on the ground is simply because I have moved a bit in the time when the light has gone and come back. Since light travels so much faster than me in my daily life motions, the discrepancy between the two times here would be so tiny that it would not be visible or measurable. And that is exactly what physics is all about things which we can measure. Of course, if instead of me just walking around the road, I had been on some, say, interstellar spacecraft of the future and been traveling nearly at the speed of light, then this discrepancy would be huge and we would not be able to ignore it at all. So, the fact that time is relative is something which is hidden from us simply because light travels so much faster than our daily life objects. But as long as we accept the principle of relativity, we have to accept that time measurements also differ from person to person or from observer to observer. And this brings us to the real lesson of the special theory of relativity. If you do not take anything away from the rest of these lectures, but just this point, that would be enough for you to embark on this new way of thinking, which will ultimately lead you towards an understanding of special theory of relativity. And this is simply the following. We must think carefully about the meaning of measuring space and time. The one reason why relativity is so difficult to understand for many people is not because it is inherently difficult, but because there are many basic issues about space and time which we take for granted, which is something which we have sort of inherited as common sense from what we see around us, which actually are not quite right. And because we do not think about those things, we just take them for granted as given to us, we often mislead ourselves. So this is the part that we have to be very, very careful about. And what we are going to do next is we are going to talk about a way of measuring space and time which takes into account the fact that relativity has given us this wonderful tool in the form of light which travels with the same speed with respect to everybody. So let me now go and describe a very simple way in which we can think of measuring space and time and use that in order to develop the full extent of the theory of relativity for ourselves. The diagram that you can see on your screen right now should be pretty familiar to most of you from high school physics. After all, who hasn't plotted an x versus t diagram? And this is exactly just that. With one small difference. Usually when you plot an x versus t diagram, you plot x along the vertical axis because that's where you put your dependent variable and t along the horizontal axis. It is a standard convention in relativity to plot things the other way around with t along the vertical axis and x along the horizontal axis. Now this actually has some obvious consequences. For example, in an xt diagram, the way you usually draw it in high school, the slope of the curve gives you the speed of a particle, and that means that the steeper a curve is, the faster the particle is moving. In this kind of diagram, things are just the other way around. The slope of a curve here, which describes the particle's motion, would actually be inverse of the velocity. So steeper curves means slower particles. In particular, if you consider a particle which is fixed at the origin, not moving at all, it will essentially be indicated by the vertical line which is the t-axis, because only the t for that particle changes, the x does not at all. At this point, it may be useful to bring in a bit of nomenclature. When we say space-time, let me point out that what we are really talking about are events, things which happen somewhere and at some instant of time. So, a point on the diagram above actually talks about a particular event, something which occurs at a particular time and at a particular place. The place, of course, is given by the x coordinate, and the time is given by this coordinate t. What I have also drawn on the diagram is a diagonal dashed line which is making an angle of 45 degrees with both the axes. And in order to understand this, let me point out that here, although I am going to keep on saying that the velocity of light is c, I am actually choosing a unit in which c is 1. What that means is I am actually measuring, say, time in seconds and space in light seconds. That is, the amount of distance which light moves in 1 second is going to be my unit of length along the horizontal axis. I could either do that or measure space in meters and time in light meters, that is, the time it takes light to travel 1 meter. Whichever way I do it, basically here, the speed of light has been set to 1 unit, and that is why the 45 degree line, the line with slope of 1, is actually something which would describe the path or sequence of events visited by a light flash which starts off at the origin at t equal to 0. Now at this point, let me also tell you that since we are plotting events, that is, we need to plot the time when something occurs as well as where it occurs, we would actually need 4 different numbers to specify such a point, and that means that it would be impossible to draw such a diagram on plain paper because that would require 4 dimensions or 4 numbers. Right now, you may have already heard that relativity makes time the 4th dimension, and we will have a lot more to say about why exactly time is the 4th dimension in the special theory of relativity. But for the time being, let's not worry about exactly what dimension means here. All we are saying is that you need 4 numbers to describe a point in space-time. And so in order to plot such a point, I would need 4 independent axes. And we can't have that. Definitely we can't have that on a 2-dimensional paper. We can't even have that in our 3D world. So what we are plotting here is really a schematic. To make life easier for ourselves, for the time being, I am confining myself to particles which can move only along one straight line, which I am going to call my x-axis. So my space is essentially 1-dimensional here, and we just have one more number, time, which I have to describe in order to specify an event. Okay, now let us try to understand how an observer who is using this particular Tx diagram would actually measure the space and time coordinates for a particular event. This observer, let us call her Alice, is actually at rest at the origin. Because she is at rest at the origin, her x doesn't change, but as I've said already, her t of course keeps on changing, which is why if you plot the sequence of events which Alice visits, you will get a vertical line which coincides with the t-axis. This collection of events which describe what a particle or an object is going through is called a world line. That's a rather fancy name, but all that really means here is that you just keep on joining these events one after the other. For Alice, who is doing the observing in this case, the world line is simply nothing but the time axis, t. The dashed line you can see on the diagram is the world line of a light flash which set off from the origin at t equal to 0. Now let us assume that Alice has a clock, or rather a wristwatch. She is wearing a wristwatch on her hand, So she can time events which is occurring right at her location just by looking at the wristwatch. And what we are going to now do is describe a procedure which she can follow so that she can measure space-time coordinates of events just by using measurements done with her wristwatch. So what she will do is something like this. At time t1, Alice sets out a light pulse. Now this light pulse, of course, travels parallel to the dashed line at 45-degree angle and then reflects off some point on the x-axis. Remember that although I've drawn a diagonal straight line, the path which light follows is straight along the horizontal axis, and once it reflects, it's going to come back. The diagonal slope that you see is simply because I'm plotting time along the vertical axis. So, what Alice needs to figure out is when and where this particular reflection took place. That is, she needs to find out the value of t, the time, and the value of x, the location at which this reflection takes place. In order to figure out how she would do that, let's follow the light flash back on its backward journey or return journey. So the light flash comes back again at 45 degrees but moving the other way and reaches Alice, that it reaches her world line, the vertical line, the t-axis, at a time t2. Note that Alice can measure the time t2 on her own wristwatch again. So both times t1 and times t2 are being measured by Alice using her own wristwatch. From these two measurements, Alice should be able to figure out the location and time at which the event, in this case, the reflection, took place. How would she do that? It's actually rather simple. Note that the light pulse has travelled for a total of t2 minus t1 time, and therefore the distance it has travelled in that interval is c into t2 minus t1. Remember, the speed of light is c for every observer. It is c, both for the outward journey and the return journey for our observer, Alice. So, the distance light has travelled is c into t2 minus t1, but note, just like the case of the flashlight shining in my hands and the mirror in front of me, here the distance which light has travelled out from Alice to the event and back in must be equal. So the distance at which the event has taken place must be half of c into t2 minus t1. And the other important thing is, because the speed of light is the same both going out and coming back in, the time taken in the two halves of the journey, up to the reflection and from the reflection to coming back, must be equal. And that means the time at which the event takes place must be t1 plus t2 by 2, right in the middle of the two time instants that Alice has measured. So this is our final result. If Alice sends out a signal at time t1 and the signal reflects and comes back to her at time t2, then that reflection must have occurred at half of t2 plus t1, this is the time, and at a position which is c by 2 into t2 minus t1 away from the origin. So, by applying the simple protocol, Alice can measure the position at which an event occurs and the time at which it occurs. All she has to do is send a light signal which reaches the location of the event exactly when it occurs and bounces back from there, comes back to her. By taking readings of when the signal was sent out and when the signal came back, she can infer the time at which the event has taken place. And, of course, where it has taken place. Now, all this looks very straightforward. This is essentially time and distance, nothing more than that. So, what is there in this formula which makes it special relativistic? The answer simply is this. The very fact that the speed of light is the same going out and coming back in is true because of the special property or special theory of relativity. In classical physics, such a thing would have happened only in one frame, the frame in which the medium in which light travels, if there were such a medium, would have been at rest. For all other observers, the speeds of light would have been different going out and coming back in, and the formula for calculating t would have been much more complicated. Come to think about it, relativity is actually easier than classical mechanics in that sense. The equations involved actually become a lot simpler simply because speed of light is the same for everybody. And what is also very important, this pair of equations is something which every observer can use to measure the space and time locations for a given event. All that they have to do is measure T1 and T2, where T1 and T2 of course are the times by their clocks when the signals left their position and went on towards the event, and the time when the signal came back to them. So this democracy between all observers, that is what special relativity gives us. Classical mechanics would have been much more difficult. The simple formula would have worked for only one observer. For everybody else, the formula would have been much more complicated. It will not be too much of an exaggeration, in fact, if I were to say that this is all that you need for relativity. Well, almost all you need for relativity. You actually need to go through one more very important thing. And in fact, that is the thing which gives this particular method that we are talking about its name. The kind of space-time measurement protocol I am talking about is called the K-calculus. Here the word calculus is used simply as a means of calculation. That is, it's a method by which you can calculate space and time coordinates of events, which is exactly what we have done right now. Well, what is this K? We are going to meet the K right now. Well, the K is the name of a multiplying factor called, obviously, the K factor. And in order to understand that, let us take a look at another space-time diagram. This is again the space-time diagram as drawn by Alice. Although I have not labeled it here, the vertical axis is still the time axis and the horizontal one the x-axis. So Alice's world line would be the vertical line. The dashed line is the world line which a photon or light pulse starting off from Alice's origin at time equal to 0 would follow. The blue line is something else. First note that the blue line is a straight line, so it has a constant slope, and as I have explained a while ago, this slope is bigger than that of the line for light. But that actually means that this object is moving slower. Just to remind you, this is a t versus x diagram, not x versus t. So, steeper a curve is, the slower the particle is moving. So here the blue line describes the world line of another observer. We had Alice, now let's talk of Bob. Bob is the person who is following this blue world line. Bob is obviously moving with respect to Alice, so his x-coordinate changes with respect to time, and the blue line captures just that. Now what Alice is going to do is something like this. She has a wristwatch on her hands, and she is just going to use that wristwatch and send light signals at equal time intervals, let's say at an interval of tau. So at 0, when Bob is right next to her, tau, 2 tau, 3 tau, 4 tau, and so on. Now, when Alice sends out those signals, Bob is going to receive them. Is he going to receive them at regular intervals? Obviously, because they are being sent out at regular intervals and Bob is moving away uniformly. But is he going to receive them at the same interval? Well, of course not. That would have happened only if Bob had been stationary with respect to Alice. Since Bob is moving away from Alice, each subsequent light signal has a longer distance to travel to catch up with Bob, and that means that Bob is going to see the light pulses at an interval which is bigger than the interval at which Alice sends them out. I'm pretty sure most of you have already recognized what this physical phenomenon is called. There is a phenomenon by virtue of which a moving observer sees a different frequency of some periodic object or some periodic disturbance. In this case, think of the light pulses as periodic disturbances, and Bob is going to measure the time interval between the light pulses as bigger than the interval at which Alice is going to send them out. So let us just see that in an animation. Bob is moving along this blue world line, and now Alice has sent out her second signal at time tau. Note that the first signal was already sent when they were at the origin. Now things are going. Alice is sending out her third signal. The second signal is now catching up with Bob. The third one is on the verge of catching up with Bob, and so on. And Bob receives these signals at times k tau, 2k tau, 3k tau, 4k tau, and so on. Note that this physical phenomenon is exactly what we call the Doppler effect. Alice sends signals tau time apart, and Bob receives them at time k tau apart. This factor k, by which the interval gets multiplied when you go from Alice to Bob, is called the k factor of Bob with respect to Alice. There is one very important point to be noted here. The time tau, 2 tau, 3 tau, 4 tau at which Alice sends out the signals are being measured by Alice using her clock, whereas the times at which Bob receives the signals, namely k tau, 2k tau, 3k tau, 4k tau, are being measured by Bob using his own wristwatch. Now, as we have already seen before, time measurement by two observers moving with respect to each other may very well not coincide. So, you have to be careful about who is making the time measurements. The time measurements in black in the diagram here, namely tau, 2 tau, 3 tau, 4 tau, are measured by Alice. The time measurements in red, the ones which are inflated by a factor of k, are being measured by Bob. So at this stage, we have all the machinery we need to embark on our journey of understanding relativity. But before we actually start deriving important relativistic principles using these very simple tools, I just need to take another look at this Alice and Bob scenario. What I'm going to say next is rather trivial and simple, but it needs to be stated, and there is a fair amount of special theory of relativity in that as well. The first thing that I'm going to talk about is what happens if Bob, instead of moving to the right as in the previous picture, were actually moving to the left at the same speed. So the picture would of course change in this manner, that the dashed line now is a line which describes the world line of a light flash starting from the origin at t equal to 0, moving to the left, and the blue line, the steeper line compared to the dashed line, is Bob's world line. Bob, of course, is moving at a speed slower than light. And the red dot, of course, as before, is Bob. Now, again, Alice can send signals out at time tau, t tau, 3 tau, and so on. But, of course, if she wants the signal to reach Bob, she would have to send the signals towards the left. And those signals would travel along world lines which are parallel to the dashed line. And this is what you are going to get. So Alice sends out a signal at time tau that goes and meets Bob at a time which, according to Bob's watch, must be k tau. Know that it has to be k tau. There's no option, because otherwise there would have been a difference between right and left. And as far as we know, space-time does not distinguish between left and right. So, because the situation should be same irrespective of whether Bob is moving towards the right or to the left, as long as he is moving with the same speed in the two cases, you should actually get exactly the same factor. So k tau, 2k tau, 3k tau and so on. Let us now go back to our original setting in which Bob is moving to the right. But the difference is that this time it is Bob who is sending the signals. Of course, Bob sends the signal at equal time intervals, let's say tau prime, 2 tau prime, 3 tau prime and so on, and Alice receives them. Now, as far as Bob is concerned, Alice is moving to the left with respect to him at exactly the same speed as Bob was moving to the right with respect to her. So because there should be no difference in the physics if you go from one observer to another, we must conclude that the situation must be exactly the same as before, and as shown, Alice must receive these signals at an interval which is k times bigger than the interval at which Bob sends them. The point is, this factor k should be the same if Alice were to send the signals and Bob were to receive them, or if Bob were to send the signals and Alice were to receive them. This again is where relativity or special relativity plays a role, because in pre-Einstein physics, the role of the two observers would not have been exactly symmetric. And again, in this sense, special relativity is a lot simpler than the corresponding classical result. Exactly the same factor k relates the two intervals. One when Alice is sending the signals and Bob is receiving them. Again when Bob is sending the signals and Alice is receiving them. The only important thing you have to bear in mind is once again that each one observer uses his or her own wristwatch to figure out the times. So in this picture, the times tau prime, 2 tau prime, 3 tau prime, 4 tau prime at which Bob is sending the signals are all marked in red. These are times according to Bob's watch. On the other hand, k tau prime, 2k tau prime, 3k tau prime, 4k tau prime, the times at which Alice is receiving these signals, they are marked in black and they are all times as measured by Alice's wristwatch. This is something you have to bear in mind. Well, now finally we have enough equipment to carry on with a full-fledged description of relativity. Now in the time left today, we will not be able to cover much, but let me at least give you one application of special relativity, which is something very new if you're not used to special relativity, that is. And in fact, it is one of the cornerstones of relativity theory. I am referring to something called time dilation. I am sure many of you have already heard of this. If not in this particular language, you may very well have heard of the statement that according to relativity, Einsteinian relativity that is, moving clocks run slow. And that is exactly what we are going to establish now using the machinery that we have developed so far. So let us consider the situation. Bob is moving away from Alice as before, and what is happening is Alice sends out a signal at time tau according to her watch towards Bob. This signal, of course, gets to Bob at a particular time, and that time is k tau according to Bob's watch. Now what Bob does is holds up a mirror at the instant this light appears in his vicinity, and so the light flash gets reflected back and turns back towards Alice. Now when will Alice receive the signal? Note that Bob could just as well have said that Bob has sent out the signal at time k tau according to his watch. So Alice must receive this at a time given by k times k tau, that is k square tau. So this is the scenario. Alice sends out the signal at time tau. Bob receives it at a time which I am calling t0. That's k tau. That of course is according to Bob's watch. and Alice receives the signal back at time k square tau. So given the fact that Alice has sent out the signal at time tau, it got reflected from Bob's position and came back to her at time k square tau, she can deduce the time and spatial location at which this reflection took place. To Alice, this particular reflection, the one which is occurring at a time k tau according to Bob's watch, must occur at a time which is midway between tau and k square tau. Remember our formula, t1 plus t2 by 2 gives you the time of the reflection. And so, the time at which the reflection occurs, according to Alice, is given by 1 plus k square times tau by 2. And this is obviously different from the time which Bob is claiming at which this particular event occurs. Actually, it's very easy to see that the time measured by Alice or inferred by Alice by her two measurements is actually 1 plus k square by 2k times the time which Bob directly records for that event using his wristwatch. So the two observers disagree about the time at which a particular event occurs. In fact, from elementary algebra, it should be very easy to show that 1 plus k square by 2k is a number which is bigger than 1, and that means that the time recorded by Alice is more than the time shown by Bob's wristwatch. Which is why Alice is going to say that Bob's watch, which is moving away, is running slow. Moving clocks run slow. But in order to place this in a more familiar context, let's also figure out exactly where this reflection took place. That's straightforward. K square tau minus tau is the time for which light has travelled. It has travelled a distance which is c times that. And because light had travelled exactly the same distance while going out and coming back in, the location at which the reflection takes place, the value x, has to be c by 2 into k square minus 1 into tau. Now notice that this is exactly where, according to Alice, Bob is at time t. So Bob's velocity, as measured by Alice, remember Bob was at Alice's origin when her clock, in fact both their clocks showed t equal to 0. So now, x by t, which is the velocity that Bob has, or speed that Bob has with respect to Alice, is given by c into k square minus 1 by k square plus 1. And so this is v, which we can rewrite in the form beta times c, where beta is simply a standard way of writing the ratio velocity of the object, in this case Bob, over the speed of light. So k square minus 1 by k square plus 1 is beta, and from here it is that very beautiful method that we all learn in algebra, componendo and dividendo, which immediately gives us k square is 1 plus beta by 1 minus beta, and k, the Doppler factor, is square root of 1 plus beta by 1 minus beta. So this thought experiment that we carried out right now told us two things. Told us that Bob's clock is running slow according to Alice, because Bob is registering a smaller time for the same event, whereas Alice is registering a bigger time. And we have also figured out exactly how much the Doppler factor is in terms of the velocity, or in terms of the v by c ratio. Now what we can do is rewrite our formula for t in terms of t0 in more familiar language by replacing the k by this expression which we have figured out in terms of beta. It's a matter of simple algebra. What you can easily do is figure out that after you plug in the value of k in the formula t equal to 1 plus k square by 2k into t0, what you end up with is a formula which many of you already know. T is given by t0 by square root of 1 minus v square by c square. So the dilation factor for time, the factor by which Bob's clock is running slow, is actually given by 1 over square root of 1 minus v square by c square. This is a factor which occurs over and over and again in relativity, and that's why it also deserves a special name. Like v by c is called beta, this factor 1 by square root of 1 minus v square by c square is called gamma. So t is given by gamma t0. Now, you may be bothered by one point here. We are talking of two distinct events actually. In fact, several distinct events, but let's focus on two. The first event is when Bob crosses Alice. This happens according to both of their watches at time equal to 0. The second event is when Alice's signal reaches Bob. Now, as we have just seen, Bob reads the smaller time interval among the two between these two events. Bob sees that the time interval between these two events is k times tau, whereas Alice sees the time interval as 1 plus k square by 2 into tau. In other words, Bob sees the time interval as t0. Alice measures the same time interval as t0 by square root of 1 minus v square by c square. But didn't we say that all observers are equivalent? Doesn't it seem here that the laws of physics seem to be different between Alice and Bob, which is why they're getting different readings? The answer is an unequivocal no. The laws of physics are exactly the same for Alice and Bob, as it must be. But the important point is, for the specific two events that we are referring to, Bob crossing Alice and Alice's signal reaching Bob, the observer, Bob, has a special role when you consider these two events. What is the special role? Both events occur at exactly the same place according to Bob. That is, both events occur at his origin. Note that these two events occur at two very different locations according to Alice. So, the first event, when Bob crossed Alice, of course occurs at Alice's origin, and Alice could see in her own wristwatch that the time at which this is occurring is t equal to 0. For the second event, however, Alice does not determine the time using a watch directly. Alice infers the time from the measurements tau and k square tau that she has done using her wristwatch. So the time interval which Bob measures between these two events is different because he is present at both events, and the time interval that such an observer measures is called the proper time interval between the two events. Now, in a way, this is a slightly unfortunate nomenclature simply because it seems to imply that the time measurement by another observer is somehow improper, but that is very far from the truth. Each observer has a perfect right to measure time the best way that he or she can. The only point is, a special role is played by an observer who can directly measure the time by using a single clock, the one which is stuck on his wrist. Some people have called this the wristwatch time, just to sort of emphasize that you can read it off your own wristwatch. Having said that, the terminology proper time is very, very standard, so we are going to keep on using it. But we are not going to call Alice's time improper time. What we will say is Alice's time is an inferred time, because she had to infer the value from the two measurements that she had done, sending out the signal at time tau and receiving the bound signal back at time k square tau. In order to emphasize the symmetry between the two observers, let us take a look at another pair of events. Alice received the bound signal at time k square tau. Let us assume that she also holds up a mirror so that the signal goes back towards Bob. When will Bob receive the signal? Of course, at time k cubed tau. But now notice that what Bob is going to say is, he sent a signal towards Alice at time k tau according to his watch, and that signal bounced back from Alice's location and came back to him at time k cubed tau. And thus, the time that he would infer for the second bounce, the bounce from Alice's location, to be k tau plus k cubed tau by 2, and that is exactly the same as k square plus 1 by 2k times k square tau. Notice k square tau is the time which Alice is inferring for that particular bounce, and that is also time interval between the very first event, that is Alice and Bob are together, and the second bounce. So this time interval is k square tau according to Alice, but note Alice is present at both events, so k square tau as measured by her is the proper time between those two events. Bob, on the other hand, is not present at these two events. He was present at the first one, but he had to infer the time for the second one, and therefore Bob is measuring inferred time, and again in this case the inferred time is longer than the directly measured time. In the previous case, it was Bob who was measuring the shorter time interval and Alice was measuring the longer time interval. Here the situation has reversed, but in both cases the observer who is present at both the events is measuring the shorter time. The time dilation formula is a very simple one to use, but one which very often causes confusion, simply because people get confused between which one is t and which one is t0. It is really very simple. All you have to do is figure out whether one of the two observers involved was present at both events, or at least whether both events occurred at the same spatial position with respect to that observer. Then and only then is the measurement of time interval by that particular observer the proper time measurement, and that is the t0 in the formula. If it so happens that neither observer is present at both events, then you cannot use the time dilation formula to relate their time measurements. You'll have to use something more which goes beyond this. In fact, you will have to use what is called the Lorentz transformations, something we are going to derive using these same techniques in a later lecture. But for the time being, let us wrap up today's lecture. We have shown how, starting from the principles of relativity, one immediately arrives at the notion that time measurements must depend on the observer, and we had figured out a way of carrying out space-time measurements just using the invariance of speed of light and basic ideas of relative motion. We have introduced the Doppler factor, and finally we have calculated the Doppler factor for an observer moving with a speed v, and as well as figured out this very important result that moving clocks run slow, and derived a formula relating proper time measurements and inferred time measurements. That's all for today. In the next lecture, we are going to further explore these and other related phenomena. Bye till then.